Welcome to Chapter 2, where we dive deep into CGCNN implementation. Crystal graph convolutional neural networks, introduced by Zhai and Grossman in 2018, represent a breakthrough in materials property prediction. This architecture specifically addresses the unique challenges of crystalline materials through edge gating mechanisms and proper handling of periodic boundary conditions. By the end of this chapter, you'll understand the edge gating mechanism that makes CGCNN special, master the handling of periodic boundary conditions in crystal graphs, learn how Gaussian expansion provides smooth distance representations, implement the CGCNN convolution layer from scratch, train models on materials project data, and learn hyperparameter optimization strategies. Let's start by examining the CGCNN architecture in detail. The paper by Zhai and Grossman in Physical Review Letters introduced several key innovations that we'll explore. The 2018 paper introduced three major contributions. First, crystal graph representation, where atoms become vertices and interatomic distances define edges. Second, a novel convolution layer with edge gating that enables distance-dependent message passing. Third, remarkable accuracy on materials project compounds with excellent predictive performance for formation energy prediction. The mathematical formulation shows how node features update. The new feature Vi at layer T plus 1 equals the old feature plus a sum over neighbors. For each neighbor j, we compute z-ij by concatenating node features v, I, vj, and edge features u-ij. This concatenation goes through two branches, a sigmoid gate and a soft-plus filter. Their element-wise product forms the message. The convolution layer architecture shows the data flow clearly. Input features from nodes I and j, along with edge features u-ij, are concatenated into z-ij. This passes through parallel branches. The gate branch applies sigmoid activation, and the filter branch applies soft-plus. Their Hadamard product is computed, then aggregated by summing over all neighbors. Finally, a residual connection adds the original features. The edge gating mechanism provides distance-dependent message weighting. This is crucial for crystals where nearby atoms have stronger chemical influence. For short distances, the gate value is high, providing strong influence. Medium distances get moderate influence with intermediate gate values. Long distances have weak influence with gate values near zero. This naturally emphasizes first nearest neighbors. Now let's understand how to construct crystal graphs properly, handling the infinite periodic nature of crystalline materials. Crystals are infinite periodic structures, not finite molecules. When building a graph, we must consider not just atoms in the unit cell, but also their periodic images. An atom near the cell boundary may have neighbors in adjacent periodic copies. Fortunately, Pymatchen's getNeighbors method handles this automatically, finding all neighbors within the cutoff radius while respecting periodic boundary conditions. Let's look at sodium chloride as a concrete example. The NaCl unit cell contains just two atoms, one sodium and one chlorine. But with an appropriate cutoff and periodic boundaries, we get many edges, reflecting the face-centered cubic coordination. Edge distances range from the nearest NaCl pair up to the cutoff limit. Choosing the right cutoff radius involves trade-offs. 4 angstroms captures only first nearest neighbors, suitable for covalent crystals like silicon or diamond. 6 angstroms includes first and second neighbors, good for metallic crystals. 8 angstroms is the recommended default from the paper, capturing up to third neighbors and working well for ionic crystals and general applications. 10 angstroms may be needed for van der Waals crystals with long-range interactions. Next, we'll learn how Gaussian expansion converts raw distances into learnable features. Instead of using interatomic distances directly as scalars, we expand them using Gaussian basis functions. The formula computes a value for each Gaussian center μk using the exponential of the negative squared difference between the distance and the center, divided by twice the variance. With centers spaced at regular intervals from 0 to about 6 angstroms, we get about 30 basis functions. This transforms a single distance value into a multidimensional vector with smooth, differentiable gradients. Visualizing the Gaussian expansion, we see many overlapping bell curves across the distance range. When a distance is input, it activates the Gaussians most strongly near its value. The Gaussian centered closest to the input distance has maximum activation. Nearby centers also activate, but more weakly. This continuous representation is much more learnable than discrete binning. Now let's implement the CGCNN architecture from scratch using PyTorch geometric. The CG-conv layer inherits from message passing in PyTorch geometric. It contains two linear layers, FC filter for the gate branch and FC self for the filter branch. The input dimension for both is the concatenation of two node features plus edge features. The output dimension matches the node feature dimension. An optional batch norm layer helps stabilize training. The message function computes the actual message for each edge. First, we concatenate the source node features xi, target node features xj, and edge attributes. The gate is computed by passing this through FC filter and applying sigmoid, giving values between 0 and 1. The filter is computed through FC self with soft+ activation. The final message is their element-wise product, implementing soft attention based on distance. A single convolution layer only captures information from immediate neighbors. By stacking multiple layers, we extend the receptive field. After layer 1, each node knows about 1-hop neighbors. After layer 2, it knows about 2-hop neighbors. After layer 3, information from 3-hop distant atoms has propagated. The paper uses 3 convolution layers, which typically provide sufficient context without oversmoothing. The complete CGCNN model combines all components. First, an embedding layer converts atomic numbers to multidimensional vectors. The Gaussian distance module expands raw distances to about 30 dimensions. 3 CG-conv layers perform message passing. Global mean pooling aggregates all node features to a single crystal-level vector. Fully connected layers with soft+ activation map to the final prediction. The total model has tens of thousands of parameters. Let's see how to train CGCNN on real materials, data from the Materials project. Materials project is the largest computational materials database, containing over 150,000 inorganic compounds computed with density functional theory. Key properties include formation energy indicating thermodynamic stability, band gap for electronic properties, elastic constants for mechanical behavior, and dielectric constants for electrical response. The API provides free programmatic access with an API key. The training loop follows standard PyTorch practice. In the training phase, we move batches to the GPU, compute forward pass through the model, calculate MSE loss against target properties, backpropagate gradients, and update parameters. In the validation phase, we disable gradient computation, collect predictions, and compute metrics like mean, absolute error, and R-squared. The goal is to achieve excellent predictive performance. The paper reports impressive performance on materials project compounds. For formation energy, the paper reports a mean absolute error of about 0.039 electron volts per atom. For band gap prediction, it reports about 0.39 electron volts. These benchmarks serve as our targets for validation. Achieving similar performance confirms correct implementation and sufficient training. Finally, let's discuss how to optimize hyperparameters for best performance. Several hyperparameters significantly impact CGCNN performance. Atom phi-len controls representation capacity, with 64 recommended but 32 to 128 reasonable. nconv determines receptive field, with 3 layers standard but 2 to 5 worth trying. h-phi-len sets fully connected layer width, with 128 by default. A learning rate around 0.001 is a good starting point. The 8 angstrom cutoff works generally, but may need adjustment for specific materials. Grid search systematically explores hyperparameter combinations. With several values for each parameter, you get dozens of combinations. Each configuration is trained, and we track the best validation performance achieved. This comprehensive search reveals optimal settings, though it requires significant compute time. More efficient methods like random search or Bayesian optimization can reduce the search cost. Beyond grid search, several best practices improve optimization. Coarse-to-fine search starts with a wide range of values, then narrows around promising regions. Early stopping terminates training when validation loss plateaus, preventing overfitting. Learning rate scheduling with reduce LR on plateau automatically decreases the learning rate when progress stalls. Ensembling combines predictions from multiple well-performing models for improved accuracy. Let's summarize Chapter 2. CGCNN uses an edge gating mechanism for distance-dependent soft attention, weighting nearby atoms more strongly. Periodic boundary conditions are essential for correctly modeling crystal structures. Gaussian expansion converts distances to smooth, learnable feature vectors. Multiple convolution layers capture information from increasingly distant atoms. On materials project data, we can achieve excellent formation energy prediction with proper training. In the next chapter, we'll explore the MPNN framework, a more general approach to graph neural networks. We'll implement customizable message functions, work with the QM9 molecular dataset for electronic property prediction, and learn when to choose MPNN versus CGCNN for different applications. See you in Chapter 3.